Welcome everybody. So today we start a new chapter in our lecture notes, namely chapter 8 on non-negative polynomials with zeros. So what is this about? So you know that for being non-negative, let's see. So if you have a polynomial that is non-negative, possibly has zeros, right? Let's say, for example, on R to the n, or maybe on some basic closed semi-algebraic subset of R to the n. When there is a certificate for this non-negativity, right? So this certificate, the first one we had learned about was if you have just non-negativity on R to the n. The first certificate for being non-negative we had learned about is that every non-negative polynomial is the sum of squares of rational functions. That was our 10th solution to Hilbert's 17th problem, right? You know, in some cases we know already that it is actually a sum of squares of polynomials. For example, if n equal 1, if I have a univariate non-negative polynomial, it is the sum of squares of polynomials. And yeah, we had, and also if I have a polynomial of degree at most 4 in two variables, right? That's what we recently learned. That was was part of Hilbert's 1888 theorem. Okay, so in general we had actually the Nicht-Negativ-Stellensatz, which said, it worked in a very general setup, so even over real closed fields. So if k less than or equal is an ordered subfield of a real closed field R, and I look at the polynomial ring over K, and when I take a preorder, that should be finitely generated over non-negative elements of K. So when I look at this, that's actually then a basic closed semi-algebraic set. It's defined by finitely many polynomial inequalities. It's a subset of R to the n. A basic closed K semi-algebraic subset of R to the n. And when we had this equivalence, f is non-negative on S, if and only if there exists this T in T. You can see this as a denominator. If you think of, you could divide by T when you get your rational function on the right-hand side, like in Hilbert's 17th problem. But anyway, this is in some way, it's a denominator, and or you could see it as a multiplier also. And if you have this TF, I find such a T in T such that TF is of this form, right? So it's f to the 2k plus t for some k. Yeah, that was a very general theorem. But now we are aiming at applications. Although we won't really get to the applications soon, but we will actually try to go towards some theorems that are good for applications. And this theorem actually, so what is one of the applications? One of the applications would be optimization. So you have your polynomial on R to the n, or you have or on some for example basic closed semi-algebraic subset of R to the n, and you want to find and say there exists a minimum or at least an infimum, right? So, and you want to compute this, right? So in our case here it would be 0, right? But I could have another polynomial which looks which looks like this, right? So what you want to compute then is, is this, so if here is another axis, just the reals, when we want to compute, for example, this minimum value here, right? This minimum value here. We would also maybe like to compute the minimizer if it exists, right? So I could say, in general, I would like to compute the infimum, where the infimum could also be minus infinity, or if you take, if you optimize on an empty set, it could also be infinity actually. Anyway, it's so you would like to minimize, right? You would like to minimize, right? So first of all, finding this minimum value, or the infimum, and then compute minimizers, maybe one of them, maybe all of them, if one exists, etc. Right? So so this so the basic strategy is that instead of minimizing, you could try to maximize the lower bound, right? That's one of the basic strategies that you can pursue in applications. So you could say, instead of minimizing, of course you could try to do this with algorithms of classical optimization, and that sometimes will work actually, right? So the problem is, however, that you can run into local minima, right? So if you do something like gradient descent, right, you just go downhill essentially, then you might end up in a local minimum and you might not get out of it, right? And if you're here in R to the n and n is big, then it's really a big problem. Of course, you could try to avoid the local minima by initializing, right, by beginning your descent in different random points. Or you take a whole grid here and you try out every point in the grid as a starting point for your descent, and by this way you could hope that you get into a global minimum, right? So the problem is global optimization. You want actually to find global optima. Whether you minimize or maximize doesn't matter too much, right? Let's say we are minimizing. Okay, so so this is, but if n is big, then taking a lot of starting points is somehow also a bit hopeless, right? Because will you really find the right starting point, right? If you have n equal 10, right? So 10 variables. And if you are looking just on all the starting points, you might say, okay, maybe as possible starting points, I take just these finitely many, all 0, 1 tuples, for example, or all minus 1, 1 tuples, or whatever. But these are already, if n is 10, these are already 2 to the 10. Might be too much, right? Okay, so it turned out that sometimes, at least sometimes, it's a very good strategy to, at least for finding the minimum value or the infimum, it can be a very good strategy to maximize, instead of minimizing the original function, you maximize a lower bound of it, right? So that means you just, you could think of this as taking a line here, right? And then you go upwards. So if I want to minimize this green function here, when I go upwards, until I hit the graph, right? And then I read off this thing here. And now you could say, why should that be any easier? That looks so how do you actually know if something is a lower bound, and how do you maximize the lower bounds, etc.? And one idea is that instead of maximizing bounds, you actually maximize certified bounds. And the certificates are sums of squares certificates very often. Could also be other things related to it, right? Yeah, and so you're actually maximizing a lower bound subject to the original polynomial f minus this lower bound, let's call it c, has sums of squares certificate for non-negativity, or has some other certificate for non-negativity. And actually, you know from the Gram matrix method that you can actually search for sums of squares certificates using positive semi-definite matrices, and optimizing linear functions over the cone of positive semi-definite matrices or over intersections of this cone with affine subspaces. That's actually called a thing called semi-definite programming, right? And so we won't go into this now, but semi-definite programming is a generalization of linear programming, if you know that, and it can be done very efficiently, right? And so using the Gram matrix method, you can actually search very efficiently for the certificates for non-negativity, right? Sometimes, but at the same time you want somehow to maximize this c here, this lower bound c, right? And that can actually be done, right? That can actually be in a semi-definite program. It doesn't disturb that c is unknown a priori, right? I don't go into the details. It's just a motivation, right? Yeah. But with the Gram matrix method, for example, you can only work with sums of squares of polynomials. Sums of squares of rational functions, you don't know how to do that with the Gram matrix method, right? And also the Nicht-Negativ-Stellensatz, I mean this one, right? You have also this denominator thing here, and you really don't know how to handle this, you could of course also with denominator, if t is, for example, the sums of squares of polynomials, then you could also search for this denominator at the same time using another Gram matrix. Yeah, you would use one Gram matrix for this if this is just sums of squares, and one Gram matrix for this. That wouldn't be a problem. Well, with f to the 2k might also be kind of a problem, but let's ignore this for a moment, right? So that wouldn't be a big problem, but the problem is that actually I'm looking for the same time, because I don't know what the minimum or the infimum is, I at the same time want to maximize this unknown c, right? And now, you know, with sum of squares here, if it is just sums of squares with t, interferes here with the c somehow. And I don't go into the details, and maybe you cannot understand it right now, but that's a big problem for this Gram if you want to search for these certificates that you want at the same time to maximize with c. If you have here this denominator, this multiplier, then that's a problem, right? That gives big problems. It's better with Schmidtens Positivstellensatz, if you remember that one. So in Schmidtens Positivstellensatz, let's see. So we didn't have a denominator, right? So where is it, by the way? It's actually not here. Here it is, right? So here in Schmidtens Positivstellensatz, that works over compact sets. So we have here basic closed K. So K is now an ordered subfield of the reals. And we have a basic closed K semi-algebraic compact set here, compact is here important. And when we have, if f is positive on f, when we have that where it exists with, but f lies in t. And here we don't have a denominator, right? So we could actually search, we could maximize c such that f minus c lies in t. So here there are other problems because t cannot be just the sums of squares here in Schmidtens positive Stanzas, otherwise s would not be compact, s would be the whole of R to the n, right? At least if n is not 0. Okay, so you know, finitely generated preorders. You know how the preorder generated by some polynomial looks like, right? So for example, you could have just one polynomial p, let's say k equals the reals here, and when I have one polynomial, right, such that the set of all x in R to n such that p of x is greater than or equal 0 is compact, right? That could happen, of course, and when for preorder I can just take the sums of squares plus sums of squares times p, right? And then I could say with sum of squares here, I implement it with some Gram matrix, and the other one also with some Gram matrix. And then actually everything is fine because the unknown c is on the other side, right? So, well, you cannot maybe know this now, but I tell you everything would be fine basically. There is just another problem because we don't have an a priori degree bound anymore on these sums of squares. Quite contrary, we have actually learned that the degree might explode necessarily for sometimes. So please look at 548, the non-existence of degree bounds for Schmidtens positive Stanzas, right? So in fact, the thing is, so of course I can then artificially restrict the degree here. I can just look for certificates where the degree of this sum of squares and this sum of squares is somehow restricted, right? So, but then it might be possible that when I want to maximize my lower bound of this green function here, right, that I restrict the degree to something, right, so that my Gram matrices are not too big, right, and I don't really get there, right, I don't really get there because the closer I want to be, the bigger the degree has to have. Look again at example 548. The bigger the degree has to get, right, and my semi-definite program becomes bigger and bigger and bigger and bigger, right? Okay, so that's one problem, of course, with Schmidtens theorem, and we won't really deal with that problem, right? We won't really deal with that problem. That's something, well, when you have to say, okay, maybe we have good luck and small degree works somehow, right? Okay. We won't deal with that problem. Another problem with Schmidtens positive Stellensatz is that with, now here I have a preorder generated by just one polynomial, right? And when I need just two sums of squares and when I need just two Gram matrices to parameterize them. But if I have now a preorder generated by 10 polynomials, because I have here a basic closed semi-algebraic set which is defined by 10 polynomial inequalities, then when you know how a preorder looks like, right? You need all products of these 10 polynomials that these are 2 to the 10 products, right? So that's a problem. That's too much, right? 2 to the 10 is too much for applications. So we will actually deal also with that problem, right? So if you have, for example, P1 and P2, so let's say we have here P1 and P2, right? And I want to look at this set. and then we'll actually look at this thing, right? And we won't, at least sometimes, and we won't always use the product of P1, P2, right? So we will look at certificates which are easier somehow, right? And when this, if we don't look at the green thing here, then this will not be a preorder anymore. That will be something which we will call quadratic module. And actually we will define today things which are even more general than quadratic modules. Okay, so often we will call quadratic module M, right? And then we will just look at, we will maximize C such that F minus C is in M. Okay, so that's something we will treat. So avoiding these products of VPIs, that's something we will treat. And another thing is that, it would really be nicer if you had a certificate for non-negativity, right? Here we don't have it in Schmidtens Positivstellensatz, you know that very well. But it would have been better if we had here a certificate for non-negativity, so that non-negativity on S implies already, okay, then of course I don't have a 1 over n here, implies already that F is in T, and okay, the backward implication is anyway true, right? So that would be really nice, right? So a denominator-free Positivstellensatz for non-negativity, right? But that's, we know that that is usually not true. Yeah, we had seen, we had discussed this here in 437C actually, right? So why would that be better? Because when, this degree explosion at least could not happen, right? So because I know that the green function here, the green function minus this yellow constant here, if I put it really here, I know that, since this is non-negative now, the green minus the yellow, I know that that this has a certificate, and this is one certificate. Its degree cannot explode because it's just 1 degree, right? So the degree I need for the sums of squares, for example, in this certificate. That's what I mean by this. Okay, that would be much better, right? And that means we would have to find certificates, perhaps denominator-free, perhaps with quadratic modules instead of preorders, that are actually valid for non-negative polynomials, especially for non-negative polynomials with zeros, because if we don't have zeros, then we have again a positive polynomial. So that's why we are concerned with negative polynomials with zeros, right? That's the ones which are very important for applications, and we want denominator-free certificates of non-negativity, not just as in the classical Nicht-Negativstellensatz with denominators, because we are looking for unknown lower bounds, right, which we want to maximize, etc. So, with motivation, I mean, you cannot understand everything because I do here this is not a course on polynomial optimization. But that I think it's important to know that going away from preorders to quadratic modules is very well motivated. Looking at non-negative polynomials with zeros is very well motivated. Looking for certificates of non-negativity that don't involve denominators or multipliers is very well motivated, and that's what we are going to do. One idea is to use our things which we have learned on convexity, and so look at this thing here. So in what we will do today, we will look, for example, polynomial rings over the reals, right? They are also real vector spaces, right? So so we can, for example, for a cone, so let's maybe make this example here. So I could take polynomial ring over the reals. I could look at it as a real vector space, right? It's a ring, but it's also a real vector space, right? And so, and I can look at cones inside, right? And for example, quadratic modules, I did not even define them. So let's maybe tell again, speak about preorders first. For example, a preorder in this ring would be a convex cone, would be a cone, right? So because it's closed under addition, it contains 0, of course, because 0 is a square, and it's closed under multiplication with non-negative scalars, because these non-negative scalars are squares, and every preorder contains all the squares, and it's closed under multiplication. So I can look at this as a cone, right? A preorder is a cone. Polynomial ring. Initially, this is the polynomial ring, but in order to apply my results about convexity, I will look at it as an R vector space. Initially, this is a preorder, but in order to apply my theorems about convexity, like this one, I will look at this as a cone, right? And then these extremal states here, right, we were speaking about. We want actually, maybe I should first show you this. We want actually we want some criteria when x is in the preorder, for example, or in a quadratic module later on. And so we want to prove that some polynomial, for example, is a member of preorder or a quadratic module. We will look at this as a cone. And when we look at these pure states of VCU, so we need first a unit, right? We need a unit, and then we will speak about these pure states of VCU. And sometimes actually this will be ring homomorphisms, right? Sometimes, right? And so we get back. For example, the Archimedean positive stanzas, we will be able to get it back from here by taking for the unit 1, right? By taking for the unit 1. Okay, the constant 1 polynomial, for example. Okay, so, yes. The problem is a little bit that if you have a non-negative polynomial, the problem is that this theorem here somehow that something stronger holds. The problem in some sense was that it was a corollary to some stronger theorem where we actually saw that if this test here succeeds, right, then actually not only x is a member of C, but actually x is a unit for C, right? So if x is not a unit for C, we don't have any chance, right? So now look again at this situation here. If we have a polynomial which is non-negative, which has a 0 somewhere, right? Then now can it actually be a unit? Unit means a unit for this cone T, for example, would mean that this polynomial f would have to satisfy that for all other polynomials p, where exists a positive integer n, such that p plus n times f lies in t, right? So, but with, if f has now a zero somewhere, right, on R2n, for example, then p could also have a zero there, or could even be negative there, right? And then this will be, if p, for example, is -1, then this will be negative in this point, right? So that means t cannot, so if this should be true, then t would have to contain elements which are negative somewhere, right? So if, for example, t would be the sums of squares, that would never be possible. Or if it's, you easily see that somehow non-negativity actually gets a problem, right? Because we need a unit in the end. And we don't, non-negativity, if you have zeros, can easily prevent this, right? And so the rough strategy then will be the following. Rough strategy will be that I go into, for example, an ideal, right? I take an ideal. So, for example, the ideal of all polynomials that vanish at the zero of f that caused problems, right? So there will be actually, the choice of these ideals will be very subtle later on. But let's just very roughly say f has a zero, with zero is a problem. So then take the ideal, for example, of all polynomials that vanish at with zero, right? And then look instead of t, and so my new vector space is actually then I. I is also an R vector space, right? That's my new, it's actually an ideal, but I look at it as an R vector space, right? R vector space. And instead of t, I look at t intersected I, right? So now what is t intersected I? Well, is no preorder anymore, usually, because it won't contain 1 usually, right? It's still a cone, right? But, well, it will be something, and with something we will now define today, right? It will be something, so we need new notions. It will still be something, but in particular it will again be a cone, right? So this we will do today. Right? In particular, it will again be a cone, right? And now we are in a better situation, see, because if you look at this, the condition that f is a unit, right? When for all p in I, right? It's a unit now in the new vector space, right? So I take only p in I, right? Right? So that's very good. That's very important. There exists an n in n, such that p plus n times f lies in t, right? Now we don't have this problem anymore, because here we take from the start a polynomial that vanishes at a given zero of f that caused maybe problems, right? So when p plus nf, actually I write here t intersected I. When p plus nf, okay, it has a zero. That's true. But p, I mean, it cannot be that at with 0 p is -1, because p also vanishes there, right? So a priori there is no problem in this condition. So the overall idea is that the polynomial ring or other rings have to be replaced by, for example, ideals, right? And the idea is that preorder or a quadratic module, we did not even yet define it, should be replaced by the intersection with this ideal. And that's when a more general thing where we will learn the notions today. And if I look in the smaller vector space, I can do much more things, right? Because I have other elements which are now units, which could never have been units in the old vector space, right? And I can then try to apply this theorem here, right? And when I will have to investigate, and we won't do this today, with extremal states, and these extremal states will turn out to be very interesting in cases like this, where I'm working here in an ideal. And the u, in fact, will somehow replace the 1, right? Whereas u used to be the constant 1 function in the old times, right? It will be now something else. It will vanish at certain prescribed points, maybe, and otherwise it will more or less behave like a very, will behave very in a very tame way, but yeah. So like a constant 1 function, if you want, not really, but so it, yeah. So this is so I think it was important to speak about rough setup, why we do this actually today, right? Because today we will only actually give many definitions and find ways of proving that some things are units for some cones, right? So whereas in the convexity chapter we completely forgot about the multiplicative structure, we didn't have one actually, we will now slowly try to reintroduce, to take up the ideas we had in the convexity chapter and to bring in multiplicative structure. What does it mean to us, right? Okay, and today we will use the multiplicative structure, for example, of a commutative ring, to find new ways of proving that something is a unit for certain cones. Okay, so today yes. Okay, so throughout this chapter, K denotes again always a subfield of R with the induced order, right? It will not be easy to work here over real closed fields, although later in the next chapter, in chapter 9, we will actually do this again, but we will actually have to work over the subring of finite elements of a real closed ring. Today, let's just take a subfield really of reals, right? That's enough for this chapter, with the induced order, of course. And moreover, we let A always be a commutative ring, and often you can think of it as a polynomial ring over K. That will be an important case, but sometimes it will be more general. So modules over semirings, right? So now, today I said we will learn about this question mark, right? What is actually such a thing, right? Or what could it be? And actually we'll be more general, we'll be even more general. Modules over semirings. It's a bit abstract. So let T be a subset of this commutative ring A. When we call T a semiring of A, if it contains 0 and 1, and if, commutative ring is always a commutative ring with 1, right? It always has a 1. If it contains 0 and 1, and if T plus T is contained in T, so it's closed under addition, and T times T is contained in T, so it's closed under multiplication. So it contains the two elements 0 and 1. Okay, if you have a 0 ring, that's just one element, because 0 could be 1, but anyway. So it contains 0 and 1, and it's closed under addition and multiplication. This looks like something very natural. If you compare this to the notion of a preorder in 1 to 1, we had that already, right? When you see for a preorder, actually, it was exactly the same definition, except for a preorder, we said that all squares should be in there. Now we say just 0 and 1, which are actually squares, right? 0 0 is 0 squared and 1 is 1 squared in every commutative ring. So a preorder, every preorder is a semiring. It's just more general. If T is a semiring of A, when M contained in A, subset M of A is called a T module of A, if it contains 0, and it's closed under addition and closed under multiplication with T, right? So it's a bit like, it's you can compare it to a definition of modules, which we won't need at all, right? So you know what is a module, although, so it's like kind of vector space over commutative ring, right? But here, I mean, we have with semiring in a given commutative ring. So, and M is a subset containing 0 and being closed under addition and being closed under multiplication with T. So you can also compare it to a definition of a cone, right? So for a cone, if you take if reals are a subring of a field of real numbers is a subring of A, and if you take for T a set of non-negative reals, then, right, you could do this. That's the same semiring in this case. When this condition just means that it's closed under multiplication with non-negative scalars. So it's also a little bit about like a definition of a cone, right? But in general, it has to do with this ring multiplication, not just with a scalar multiplication. Okay. So remark 8128, T is a preorder of A if and only if T is a semiring that contains all squares. And as I said, was 2 squares, 0 and 1 anyway are already contained. If T is a semiring of A, when T minus T, the set of all differences of elements of T, is a subring of A. Well, it's a subgroup of the additive group of A, right? Because it contains 0, right? And it's closed under addition. So it contains 0, sorry. It's closed under addition. Right, so this is right, and it's closed under inversion, right? So additive inversion. So or maybe I write it with. So. Right. So so it's a subgroup of the additive group of A, and it contains and it's closed under multiplication, and it contains 1. Right? Why is it closed under multiplication? So using distributivity. So it's contained in T times T minus T, T minus T, T. Minus times minus gives plus, so plus T is contained in T minus T minus T plus T, and this is contained in T minus T. Okay, and it contains 1 because 1 is an element of T, and therefore also of T minus T. So it's really a subring of A. Okay, so now if you have module a T module of A, so if M is a T module of A, okay, T has of course to be a semiring of A then. when m minus m is a t minus t module of A. So in order for that to be true, t minus t has to be a semiring. Actually, it's even a subring of A, but in particular, it's a semiring, right? So, and when we have to check, this here, right? So that 0 lies in m, but 0 lies, that 0 lies in m minus m, but it lies even in m, and m is contained in m minus m because 0 lies in m. That m minus m is closed under addition, it's very, very easy, and that it is closed under multiplication with t minus t. Maybe let's do that one. So t minus t times m minus m is contained in tm minus t m minus tm plus tm, which is contained, since tm is contained in, since m is a t module, tm is contained in m, right? So therefore this is contained in m minus m plus m, and that's contained in m plus m minus m plus m, which is contained in m minus m, because m plus m is contained in m, and because, and that's it, right? Okay, so m minus m is a t minus t module of A. Okay, then if T is a semiring of A, then T is a T module of A. Okay, let's look again at definition of semiring, right? And T is then a T module, so just here we have M, but we have the same thing here for T. M plus M is contained in M. Well, we have T plus T is contained in T. 0 in M. Well, we have 0 is in T, right? So it's a T module. Okay, and next definition: let T be a semiring of A and M a T module of A. When M is called Archimedean in A, if for all A in A there exists an n in n such that m plus a lies in m, right? This doesn't come as a surprise. Let's look at 4, 1 to A. 4, 1 to A. That was exactly the same thing. Here we had a preorder in a commutative ring, actually, and we called it Archimedean. If and only if we have exactly the same condition. Now instead of a preorder in a commutative ring, now we have a semiring in a commutative ring. We have actually a T module in a commutative ring, which is much more general, right? But otherwise, it's exactly the same definition. Note that we have now also defined not only the notion of an Archimedean T module or an Archimedean module over a semiring, but also the notion of an Archimedean semiring, right? Because T is a module over itself, right? A semiring is a module over itself. So that's why we have also defined now the notion of an Archimedean semiring. And semirings were just generalizations of preorders, and that's exactly a generalization. So Archimedeanity is exactly defined in the same way. So it's compatible with our definition we have already for preorders. Okay. So that's what I write here. The notion of an Archimedean semiring is also defined by this, right? Because of this, because semiring is a module over itself. yeah, and this generalizes the notion of an Archimedean preorder, right? Because semiring, every preorder is a semiring, right? And Archimedeanity means the same. Okay, good. So now definition 815. So we define the set with respect to M by U arithmetically bounded elements. If U is an element of A, right? So U is an element of our commutative ring A. And I have a semiring and I have a module over with semiring. Very general setup, right? Just abstract. For example, I could just, instead of M, I could just look at T itself, because T is a semiring over itself, right? So if it makes it easier to understand, when first think of just M being equal to T, so T is just a semiring of A. And then, and you know, that's a generalization of a preorder, right? So you might even at first think of a preorder, right? And then for you, you might, in order to understand it better, you might, at the first moment, you might of U equal 1, right? So when, if U equal 1, then actually what we define here, a set of all A in A such that there exists an N in N such that N times 1, so that means N, plus or minus A, lies in M. That's actually something we had called, in the case where T was a preorder, we had called this the set of arithmetic set of elements that are arithmetically bounded with respect to this preorder, right? So now here we have a generalization. So T can be a semiring of A. It can even be a T module of A, where T is a semiring, right? And U not necessarily has to be 1. So U can actually be anything, right? So when we say it's arithmetically bounded by U, okay? But the idea is the same, so a U replaces somehow a 1, that's always the idea, right? The notation is now BAMU, whereas before it was BAM. So let's compare it to 3, 4, 1, so that, yeah, so that we really see it's just a generalization, a very vast generalization, right? Yeah, and you remember that this here it was actually a subring of A. We had to prove this, right? Now the question is, which properties does it have now? We will be concerned with this for a while. So, yeah, and we used this fact that it is a subring actually, and yeah, you know, we used this set of arithmetically bounded elements with respect to a preorder. We used it in order to show that some preorders are Archimedean, right? That was actually a tool for showing that some preorders are Archimedean, right? We used this as a tool in this characterization, for example, of Archimedean preorders. So that was very, very important, although it's very easy things, right? So now that was just a definition, and so now the next proposition, suppose T is a semiring of A, M1 and M2 are T modules of A, U1 is in M1 and U2 is in M2, then I can build all finite sums of products of an element of M1 and M2, and this is also a T module of A, right? So why is it? So let's perhaps first check this. So it contains 0. Well, because you could take here the empty sum. So it's closed under addition. Well, that's obvious because here I take finite sums of such things, right? Finite sum plus a finite sum is again a finite sum, and t times m is contained in m. Well, that's also easy, right? So t times such a thing. Well, when you can put with you can put with multiplier. You can hide it in m1 or in m2 as you like. So that's also okay. Right? It's a bit like the product of two ideals, right? If you know about that thing. Okay, so now important thing now is that if I have an element which is arithmetically bounded with respect to m1 by u1, and I multiply it with an element which is arithmetically bounded with respect to m2 by u2, when I get an element which is arithmetically bounded with respect to this sum m1, m2 by u1 times u2. Okay, this looks extremely technical, right? Okay, but the proof is not hard, and it's actually practically the same proof as in 431 when we proved. When 431, the hard thing to prove was, of course, I mean, it was not really hard, but the essential thing we had to prove is that products of arithmetically bounded elements are arithmetically bounded, right? And for this we used this identity here with 3n squared plus ab, n is a positive integer, a and b are in a. I mean, n squared actually is interpreted, of course, as n squared times 1, so it's 1 plus 1 plus 1, in this, where 1 is the 1 from the ring. So 3n squared plus or minus ab, respectively, is n plus a times n plus or minus b, respectively, plus n times n minus a plus n times n minus or plus, respectively, the other way around, right? If I have here plus, I need here minus times b. We had proven this here. And here we take exactly the same identity, except that we have somehow to use the units. Okay, maybe let's make a copy of this. So that we really see it's the same thing. Oh, so, okay, so let a1 be arithmetically bounded with respect to m1 by u1, and a2 with respect to m2 by u2. So I have these two ai's here for I in 1 or 2. So when, say, we have n ui plus and minus ae lie both in mi, and actually, yeah, you know, I for I in 1, for I equal 1 or 2. So a priori that the a1 and a2 satisfy this would mean that there is an n1 and an n2, right? But when I can take the maximum, right? Because I mean, yes, because I have here that u1 and u2, u1 is in m1 and u2 is in m2, right? I can just add, if I have something like this, then I can increase the n here, right? By just adding another ui here, right? So that's why I can suppose I have the same n here. It makes it technically a bit easier. Then I have, okay, I did not copy the right thing. I wanted to copy the identity. Okay. Okay, then I have, now it gets a bit more complicated when here, where here is 3n squared times 1 times 1, right? I have here, you know, u1 and u2 here are 1 in some sense, right? I have here 3n squared u1, u2 plus or minus a1, a2. equals n u1. Instead of n times 1, I have n times u1. Here instead of n, I have n times u2. And here I have n times u2 instead of n, and n times u1 instead of n, and here in the same way. But otherwise it's the same, right? Okay, so now let's just check it. Let us just check it, right? So, okay. Yeah, so a 3n squared u1, u2, where is it on the right-hand side? So 1n squared u1, u2 is actually here by combining these two, right? By combining these two. That gives 1. The other one is here, right? If I multiply this with this, right? And the third one is here, right? So this gives this 3n squared u1, u2. Now, what about the plus or minus a1, a2? Well, let me draw this in green. That's these two multiplied together. Okay, actually with the signs, right? Okay, so that gives this here. Now the problem is that I get here mixed terms, right? So I get nu1 plus or minus a2. But this is neutralized by here, nu1 minus plus a2, right? And I get also the other mixed term here, a1 and u2. But that is subtracted here again, nu2 minus a1, right? So yeah, that shows this equality here. Okay, so that was like a very technical proposition, but also very useful. So corollary of this is now, let T be a semiring of A, M a T module of A. So actually what we do here is that this M takes the role of a second M2 here, right? So instead of M2 and U2, I have now M and V. And the role of M1 is taken by T itself, because the semiring is always a module over itself. So T takes the role of M1, right? And then I have here, but when I need this, instead of U1, I have U in T. And then instead of this, I have an BATU, right? The set of elements arithmetically bounded with respect to T by U. Now this product here is contained in, so here so the sum, if M1 is T itself, then, T times M2 is contained in M2. On the other hand, M2 is contained in T times M2 because 1 lies in T, right? Because T is a semiring. And so in this way, you actually see that you get here just M in this case, right? This sum here just gets M. And here I have a product of these two elements. Yeah, and so I see that... So now we look at a special case where we have here for U1, right? 1 is actually always in T. If T is a semiring, so I can actually then forget about this hypothesis here. And I have here B of AT1, right? And here I have just 1 times V, so I have just V. Okay, so that has the advantage that I have here twice the same thing, namely the set of elements arithmetically bounded with respect to M by V. And here I have a set of elements arithmetically bounded with respect to t by 1. And by 1, actually, I don't need to specify it if I mean by 1, when I just can omit the by 1, right? And actually, we wrote also, for this, we then just wrote b of at, right? So that was, you know, yeah, that was actually this, it was this part of this definition 815, right? Actually, if t is a preorder, we had defined this object earlier already, but this is compatible here with this more general definition, right? So we see that, okay, so let's now look. So let t be a semiring of A, when BAT is a subring of A. Okay, why is it the subring of A? Well, it's closed under multiplication. You see this, namely, if you take still a more special case, if you take here for m equal, if you take here m equal to t, because t is a t module of A, and for v we also take 1, right? So I can forget about this hypothesis. When I have here also 1 and 1, and then I have here BAT and BAT. So I see that the set of elements arithmetically bounded with respect to a semiring T is multiplicative, is closed under multiplication. Okay. And, well, it's also... it's actually very, very easy to see that it's also closed under addition. Do this as a little exercise. That it contains 0, that it is closed under additive inverses, right? That's clear because, you know, if nu plus minus a lies in m, then nu minus plus a lies also in m. And so it also contains 1, if so 1 plus minus 1 lies actually always in t, right? Because 1 plus 1 lies in t and 1 minus 1 lies in t. Because 1 minus 1 is 0 and 1 lies in t, and so because t is closed under addition, 1 plus 1 lies also in t. So so I see here that BAT is a subring of A, and actually now if I go into a more general case here, I see that yeah, that BAMU is a BAT module of A, right? Because what does this mean? It's closed under addition. That's again easy to show, very easy to show, and yeah, and contains 0, easy to show, and yeah, and this is the condition, the crucial condition, right? Which we have just shown, right? Yeah. You know, this is not just a semiring in A, it's actually a subring of A even, but that's okay. And this, by the way, is also closed under additive inverses, but we don't need this here for this statement. Yeah, anyway, so remark. If T is a semiring in A and M is a T module in A, when M is Archimedean, if and only if every element of A is arithmetically bounded with respect to M, right? In fact, I think that here is some subtlety. which so I think here I should say here with 1 in M. Yeah, I should here, 1 does not have to be an element of such a T module, right? That's not required, but here I want to require it, right? Why do I want to require it? Because Archimedean initially by 813 means this condition here, right? Whereas that every element is arithmetically bounded with respect to M means actually that I have here plus or minus. Now you might say, why does that matter? Well, of course, if that's true for all A in A, then it's also true for all minus A. But the problem is for minus, the N might be a different one, right? So I have N1 plus A lies in M, and N2 minus A lies in M. Now, I said several times already in at other places that when just take the maximum N, so you get the same N for both, right? The same N for plus or minus A. But that argument probably requires that if I want to add here a 1, for example, if I want to take here N plus 1 instead of N, well, when I can do this certainly if 1 lies in M, but otherwise I don't know how to do it, right? So I think we use here 1 in M. Anyway, I'm requiring that now here. Okay. So, the next theorem is a characterization of Archimedean semirings, right? In 434, we had for preorders something similar, right? So here K was an ordered subfield of reals, right? Here it's also a subfield of reals with the induced order, so that's the same thing. So, and here we had a preorder containing the non-negative elements of A, and then we had that the following are equivalent T is Archimedean, and there exists an N in N such that for all I, N plus and minus xi lie in T, right? So I have here, condition is here that 2n elements lie in T. You could think of these as polynomials where the corresponding inequalities would define a cube, right? So, if you look at the system of 2n equations, n plus minus xi is non-negative, right? Yeah, and here in 434 I had this the second condition which I don't have now, which says which takes a ball instead of a cube, right? A ball with radius square root of n, right? Okay, so but here I have again this cube condition, right? If you think of T as being the polynomials that have a certain certificate of non-negativity on some set, then this means that here I have a certificate for this set being contained in a cube, right? And so as I say, so that's again the cube. So this time I don't have a ball, I have something more complicated. So I actually have linear polynomials, so polynomials of degree at most 1. So in T, and so this would then define, you could call this a polyhedron, right? And this polyhedron should be bounded. because of this n, and so that's an additional boundedness condition here, right? So yeah, and so, but otherwise it's the same thing, right? Instead of this cube, I take now a bounded polyhedron, right? Yeah, don't know how to draw it, right? Etc. Right? So instead of such a thing, I take now such a thing, but it should be bounded, right? So yeah, and again, the LIs should be, if you think of T as being those elements which are in a certified way non-negative on some set, when this means that this set is in a certified way contained in such a bounded polyhedron, right? Whereas here I have a cube. Okay, good. So this bounded polyhedron in some sense replaces what in 434 was with sphere, right? With radius squared in, right? So yeah, so it's not as nice. It looks much more complicated, but the idea is the same, right? So, so write A to be this polynomial ring because when the negative elements from K are contained in T by hypothesis, it easily follows that, because K was a subfield of reals, it easily follows that K, every element of K is arithmetically bounded with respect to T, and hence we have that BAT equals to A if and only if, because K is already in this subring, right? BAT is a subring of a polynomial ring containing now already K. So it's the whole polynomial ring if and only if it contains every variable, of course, right? So we have to show that, Archimedeanness is equivalent to every variable here being contained. And, but that's equivalent, for, that's actually equivalent to, for all I, where exists an n, right? But because 1 is in T, if for every I there exists an n, then there also exists an n such for every of these finitely many i's, etc., right? So that shows actually A if and only if B. Implication B to C is trivial. Just take for the Li's, just take m equal to n and take for the Li's the n plus minus xi, right? And C to B, okay, by the way, this bounded polyhedron, I didn't say this should be non-empty, that's also important, right? And C implies B is an easy consequence of a linear nicht negativ Stellensatz 7/22, and here I need now this non-emptiness because here every n plus minus xi, because of this inclusion, every n plus minus xi is non-negative here on this polyhedron. But by 7/4/22 there is then a nice certificate, but that's because because I have here the non-emptiness, right? I need this here. So the n plus minus xi are non-negative on this set, and therefore I have such a certificate, and the non-negative elements from K are contained in T. So so I see that where n plus minus xi line t. Also using that we alias line t, of course. Okay, good. So the next lemma is about, shows that in some sense this set of elements arithmetically bounded with respect to sums of squares module. Let me call this now sums of squares module. You know that, suppose that 1/2 lies in A, that means 2 is invertible in A. 2 stands for 1 plus 1, of course, right? So then, the sums of squares build, of course, a semiring, right? Because they are a preorder when they are also a semiring. And and I can look at modules over with semiring. So that, let me call that the sums of squares module, right? That contains 1, actually, right? So actually later I will call such a thing, such a sums of squares module, which contains 1. I will later on call it a quadratic module, but for the moment, that's okay. And let A in A, when A squared is arithmetically bounded with respect to M, if and only if A is arithmetically bounded with respect to M. So, yes, there are two things to show here. BAM, I don't see any reason why it should be closed under multiplication, so even the direction from right to left does not seem trivial. So, but of course, maybe the main application will be from going from left to right. Compare also 432. 432. Right, so here we had, here the direction from right to left was actually trivial here, because here BAT was actually a subring. But here also, by the way, we needed 1/2 lies in A, and when we had also this implication that A squared is arithmetically bounded with respect to T when A is also. So here we have now this much more general, and we have also the other direction, which in this case is also not completely trivial. So, but it's not hard. So for the direction from left to right, if n is in n such that n minus a squared lies in M, right? When for technical reasons, let me exchange n by n plus 1, and then I have here n minus 1 minus a squared lies in M, right? So I use here just that n minus 1 minus a squared lies in M. I don't use that plus a squared lies in M, because that's anyway trivial, right? Because here I have a sum of squares, 1 is 1 squared and so on. And here I add another square, and 1 is in M, so M contains all sums of squares anyway. So the plus is here isn't interesting. Interesting is only the minus here, right? So, but if I have this, right, and I have this, I can find such a positive integer, and if a squared is arithmetically bounded with respect to M. When I want to show that A is arithmetically bounded, and that's exactly as in the proof of 432. So let's look at that proof again. So that was exactly the same trick. So okay. Okay, so it's exactly the same trick. So n plus or minus a is n minus 1 minus a squared, which lies in m, plus 1/2 plus minus a squared, because that's a square, you know, in squares lies in m, because 1 lies in m, and it's closed under multiplication with squares, and plus 3 times 1/2 squared, you know, that's again, that's, well, 1/2 squared is a square, and m is closed under addition, so 3 times this is also in m. Yeah, so, yeah, and why this identity is true for the same reason it was true before. So I have here the n, which is here, the minus plus or minus a comes somehow, you know, if I take here this times this and the other way around, right? This gives me two mixed terms here, which I add up to the same thing. And they add up to this plus or minus a. And now I have here minus 1 minus a squared. Yeah, but that's, you know, I get here a squared here from a non-mixed term, and here 1/4. And here, yeah, 1/4 plus 3 times 1/4, so that gives actually 1 then. Yes, and together, you know, with, yeah, so a blue thing, so together with this minus 1, this is neutralized by this minus 1, right? And here I have here a squared, minus a squared, which neutralizes this a squared here. And yeah, so I get, all in all, I get that I get this equation here and this equality here, and so n plus and minus a lies in m. Okay, so that was one direction. For the other direction, if we have n in n with 2n minus 1 plus or minus a lies in m, you know, I can, without loss of generality, I take here an odd number, because if I have an even number, then, well, I can just add 1, because 1 lies in m. Okay, so if a is bounded, then I get this odd number 2n minus 1 here. And then now it gets a bit tricky, so actually the other direction seems even a bit harder now. Didn't expect this. Okay, so n squared times 2n minus 1, so that's, anyway, that's a positive integer, minus a squared. I have to show that that lies in m, right? Because if I take here plus instead of minus, then anyway it lies in m, right? That's anyway trivial. But so minus is the important thing. And now comes a tricky expression. So let's analyze a little bit. So y is, first of all, y is this equal. Second, why does it lie in m? Well, 2n minus 1, why does it lie in m, maybe perhaps first? Well, because I have here 2n minus 1 plus a lies in m. So this lies in m. And also the same with minus a lies in m, so this lies also in m here. So this lies in m. Okay. Now here, that's a square here, right? So these products here lie in m. So if I add them up, it lies in m. Here I multiply with another square. And here times 2, that's also okay, right? Because, I mean, taking times 2 means just adding the thing to itself, and then it's closed under addition. Okay, so that's it. So that shows why this lies in m. And now why do we have this equality here? Okay, so you see that, yeah, so I have here, let's just calculate a little bit. so the terms which involve an a on both sides, what are they? So let's analyze a little bit what terms. So if I expand everything on the right hand side here, what terms do I get that involve a? Well, I have here, maybe I write this here like, so it's n squared minus 2an plus a squared, and that's n squared plus 2an plus a squared, and okay, so now maybe I do it like this. I write it like this. Okay, so I have here the n squared plus a squared. I have it here and I have it here, right? And if I multiply this with 2n minus 1 here in both cases. That gives then yes, and so I get twice this thing, right? I get twice n squared plus a squared times 2n minus 1. But here I multiply with 1/2 here, right? So I get actually n squared plus a squared times 2n minus 1. Okay. If I multiply this non-yellow thing with 2n minus 1, this is neutralized with this, because here I have minus and here I have plus, right? So now I have to care only about taking from this expression here the a here, right? So here it's exactly reverse. The yellow thing times a neutralizes with the yellow thing times minus a. So here I have to take care about this thing here. So minus, here I get minus 2a squared times n. And here I get the same thing again. So, but when I divide here by 2, so I get in fact minus 2a squared divided times n. So now this, so right hand side is actually equal to this, right? Now I can expand this here when I get a squared times 2n minus 1. Minus 2 yeah, so that's 2a squared times so maybe just let's calculate, cannot be so hard. So that's 2n, maybe it's n squared times 2n minus 1 plus a squared times 2n minus 1 minus 2a squared times n, right? And this here, that's 2n a squared minus 2n a squared minus a squared. Yeah, so I get exactly this left hand side here. So using this, we can now prove the following very technical very nice proposition. So okay, so one proposition is as follows. Suppose 1/2 lies in our commutative ring A, so that means 2 is invertible. Okay, and let T be a preorder in A. For example, it could be the smallest preorder that exists, namely the sums of squares, consisting exactly of the sums of squares. And let M be a T module containing 1. So, for example, T could be, again, the sums of squares, when M would be a sums of squares module containing 1. Later on, we will call such a thing a quadratic module. But here, it can be a T module, and when BAM, so the set of elements that are arithmetically bounded with respect to M, right? By 1, if you want to say this, right? You can omit this. Is a subring of A, and BAMU for each U in T is a BAM module of A. Okay, so that actually this seems quite surprising. It obviously suffices to show that BAM times BAMU is contained in BAMU for all U in T. Since 1 is in T, and then I have in particular this one, with inclusion, meaning that BAM is multiplicatively closed. And it's clear that BAM contains 0 and is closed under addition, right? And when, if you look up again the definition of T module, right? I mean, BAM is actually a subring, but in particular it's a semiring of A. If you look that up, then you see that this is enough to show that 0 lies in it's 0 lies herein, and it's closed under addition, which is clear, and it's closed under multiplication with elements from this thing. So it's enough to show this for all U in T. So fix an A in BAM. When we can, so the trick is that I write A, essentially as a difference of 2 squares. Like this, because 2 is invertible, I can here divide by 4, so that's okay. And 1/4 is actually a square. Because T is a preorder, it contains the squares, right? And so, because 1 lies in M, we see that if A is in BAM, then also A plus 1 and A minus 1 are in BAM, right? Also easy to see. Yes, therefore it is enough to show that, it's enough to show that BAMU is closed under multiplication with squares, right? Because an arbitrary element from BAM, I can write it like this. And so it's enough to show that BAMU is closed under multiplication with squares, right? So for this A squared, I can first take the A plus 1 squared, then the A minus 1 squared, and I also use that BAMU is closed under taking additive inverses, which is clear, right? And then, So anyway, it's enough to show this. You can easily reduce it to this. for all A in BAM and U in T. So for this purpose, now fix again an A in BAM again, right? And U in T, fix also U in T, and B in AMU, when we have to show that A squared B lies in AMU. Now from our marvelous lemma here, we get, from this lemma, let's copy this. So from this lemma we get that since we have that A squared, since we have that A is in BAM, we have also that A squared is in BAM, right, from the lemma here, right, because M is actually also a sums of squares module, because T is a preorder and contains the sums of squares, therefore, right? And M contains 1, right? So we have A squared is in BAM. So, but then we can choose an N in N such that N minus A squared lies in M. And at the same time, NU plus N minus B lie in M, right? This N a priori would be different from that one. I mean, here I use that B is in BAMU. But since one is in M, we can take the maximum of both, and it works for both. Due to A squared and U in T, right? Why is U in T? Well, that was that was like we fixed it here, right? And A squared because T is a preorder. And now since M is a T module, I can multiply here with, U from the left, right? I mean, left or right doesn't matter because we are in a commutative ring. So we can multiply with U, and we get NU minus U A squared, lies in M again. And here we multiply with A squared. Again, because M is a T module, then we have here NU A squared plus A squared B plus or minus A squared B lies in M. Consequently, so now, wrapping everything up, so N squared U, plus and minus A squared B. Yeah, we have to show that this B, A squared B lies in BAMU. That would be, we are done if we can show that this lies in M, because, N squared is a positive integer. Okay? And, so this is, let's see, so this is N squared U again, right? When minus NU A squared plus NU A squared, right? Plus minus A squared B, right? And now, but now with N squared, here I can, yes, this is, I mean, you could write this like this. You can factor out the N here. And when you have here, that's just NU minus UA squared, which lies in M, added several times to itself, right? M is closed under addition, so this is again in M. And this here is exactly this thing here, right? So that lies in M, so M is closed under addition. So all in all, this is in M, and we are done. Okay, so this looks quite technical, but now we come to finally to a theorem, and this can be compared to 8.1.10. So let's see. So here, you know, we had this theorem that was the characterizations of Archimedean semirings in the polynomial ring here over a subfield of reals, and namely Archimedean semirings containing the non-negative elements from the subfield. So here we had these three characterizations, right? Archimedean, here with cube condition, and here with bounded polyhedron condition. And we have the same thing here for weighted sums of squares modules. Let me call this the weighted sums of squares modules. So I have weighted sums of squares where the weights are non-negative elements from K, right? In many cases, if K is the reals, for example, you don't need these weights, of course, because you can hide them in the squares here. So if you have a weighted sums of squares module containing 1 in this polynomial ring, then you have again exactly the same three conditions. I mean that one, and that one. Here the cube condition, the bounded polyhedron condition, and you have again the ball condition here again, right? So that's that works again here. Okay, so we have all of them now. Okay. So so A to B is, so that in particular, you know, that that in particular contains the case of where if M is a preorder containing negative elements from K, then when this can be applied again. But in 434 we had already, for preorders, we had already the same thing, except that we did not mention here the bounded polyhedron condition. At that time we did not know yet the linear nicht Negativstellensatz, so right. But here it's much more general, because it's you know, M does not have to be closed under multiplication actually. Okay, so A to B is trivial. You know, yeah, again, maybe I say again, what is, yeah. First you would perhaps get for all I where exists with N, right? Yeah, but then you can say there exists an N for all I, because 1 is in M, and you can just increase the Ni's which are too small somehow, right? And you can take the maximum of finitely many N's. Okay, from B to C, if B holds, then n minus xi squared in M for each I, right? Because I can just add, you know, I can just add the sum of the xj squared where j is different from I, because M contains 1 and therefore contains all squares. Okay. And so you have n minus xi squared in M. Anyway, you have n plus xi squared in M, because 1 in M. So you have actually that xi squared is arithmetically bounded with respect to M, and that you have for all I. And now we apply 8111 in the other direction, so namely the direction which says if a square is arithmetically bounded, then the thing itself is also. If a square of something is arithmetically bounded, then the thing itself is also. So we see that because we see that xi is arithmetically bounded for each I. And then I can take here again the same n for the argument, for the reasons I have already mentioned. Because first you would get for all I there exists an n, but now we have there exists an n for all I. That's okay. Then from C to D, this is trivial. just take for VLIs, just take m again to n, and for VLIs you take Vn plus minus xi. And when for n you take n. Okay, and when D, we have to prove D implies, we will actually prove D implies C, and then finally C implies A, right? Where it closes the circle. Why do we have D implies C? Well, this follows again from a linear Nicht-Negativ-Stellensatz 7422. Here we use that when non-negative elements are in M, because these are the multipliers you need in the linear Nicht-Negativ-Stellensatz. We also use again that 1 is in M. We also use that this is non-empty here to apply the linear Nicht-Negativ-Stellensatz. And from C to A, so if you have now this cube condition, why do we have Archimedeanity? That's because Archimedean means that BAM is everything, but we know that from 8.1.12 we know that BAM is a subring, right? And so we see also that it contains K, right? Easy to see that comes from the fact that non-negative elements from K are contained in M, and so it suffices to show that it contains every xi, but that's written here, right? Every xi is arithmetically bounded with respect to M. Good. So this was a bit technical, but will help us a lot, right? This section. So thanks for listening. And I hope you stay with us. Thank you. Goodbye.